Thanks for the introduction. Hello, everybody. I'm glad to see all of you this morning. I'm Adnan. The work I'm going to present today was done as part of my master's thesis, so let's start. So I'll begin by giving a brief description about the problem we are trying to solve. The regular expression denial of service, otherwise known as REDOS, is a denial of service attack. It exploits that most regular expression engines which use the backtracking matching algorithm may reach extreme situations that cause them to work very slowly due to ambiguity in the regex. Here's an example of a REDOS regex that was found in Microsoft email server. When an attacker crafts a malicious input for this regex, it runs very slowly on the server. And imagine doing that from thousands of places around the world at the same time. It might even take 100% of all the CPU resources. This will create a denial of service situation, which means when a normal user comes, the user will not get any service as all of the CPU resources are taken. This is how regex denial of service works. Some high-impact outages due to regular expression denial of service includes one in a Stack Overflow, which caused a 34-minute outage, and a recent one in Cloudflare that caused a 27 minutes outage. So now, as almost all of the web is regex-based, regexes are used all over the stack. Therefore, REDOS can happen at any places. Next, we will see some previous works in this domain. Given the severity and prevalence of REDOS, many approaches have been proposed to address the problem. Our work builds on those that try to detect and fix those regexes. In this vein, some tools proposed to detect vulnerable regexes, which includes automatic techniques and anti-patterns, and some researchers also proposed to fix these vulnerable regexes. Now, all of these approaches have been evaluated solely via automatic experiments. However, literature shows that developer tools may not be adapted if they lack usability. Now let's see how we improve on these past works. The goal of our work is to improve the usability of existing REDOS defenses. Our insight is that the usability of existing tools to detect and fix regexes will improve if we complement the detection tools with anti-patterns that explain what part of a regex makes it vulnerable to REDOS, and complement fixing tools with fixed strategies that the developer have used in the past so that they can choose a fix that they will understand better. We specifically aim to improve developer understanding of the outcome of the tools. To be able to produce our anti-patterns and fix strategies, we first build a novel ambiguity theory to precisely and completely model regexes that are vulnerable to REDOS. Now, the core three operations engineers use to encode regexes are concat, star, and alternation. By building the theory, we found that only concat and star can lead to infinite ambiguity. Therefore, we designed our anti-patterns around the concat and star operations. Also, we developed 5 fixed strategies. Those can be applied to any of the anti-patterns. For the time constraint today, we'll not be talking about our ambiguity theory and how we prove the theorems. You can find those in our paper. Now, let's see how we develop those anti-patterns and fixed strategies. So as you have seen before, we have developed 6 anti-patterns and 5 fixed strategies. But in today's presentation, we'll only show 1 concat and 1 star anti-pattern, and we'll show how we can fix these anti-patterns with 2 of our fixed strategies. You can find the rest in our paper. Now let's see 2 of the anti-patterns. So we'll start with concat 1. So it says that if a regex have a sub-regex P star Q star, and the quantified parse P star and Q star can match some shared string, then the regex will be vulnerable to REDOS. Now, if P here is represented by /W, and Q here is represented by /G, for example, the resulting regex would look like /W star /G star. Now, /W means it can match any alphanumeric character and underscore, and /G means it can match digits. Now, both of these can match digits, right? Now, if we have a malicious input, which may be like thousands of 6 that ends with exclamation mark, now /W or /G, none of these can match the exclamation mark. So in case of mismatch, what it would do for each 6, now for each 6, the Regex engine has 2 options. It can use the /W or it can use the /D. So it tries all of these options for all of those, and thus the regex matching overloads the CPU, causing regex denial of service. Now let's see the example of *1. So if we have a regex with a star, and inside the star element, there are a bunch of alternations, and between this alternation, there will be some intersection. Now, if we represent P here with /W and Q here with /T, the resulting results would look like /W or /G star. Now, as you have already seen, with /W and /G, we can match alphanumeric characters underscore and digits, respectively. Now, both of these can match digits, right? So if we use the same malicious input, which is thousands of 6 that ends with an exclamation mark, so for each 6, we have two options. We can match it with the /W, or we can match it with the /T. So when the engine sees a mismatch, it tries all the options before it says, OK, I cannot match it. So this is how the denial of service will happen here. So how can we fix this? So let's see how can we fix these anti-patterns we just saw. So if you remember from the previous slide, we saw two anti-patterns, concat1 and star1. And these are the vulnerable regexes that we saw for those anti-patterns. So our first fix is reduce one of the sub-regexes, P and Q, so that it no longer matches any of the shared string. Now, if we, so here we have two quantified parts, like /W and /D. So if we say that, OK, let's reduce /W to match only letters and underscore, then there will be no overlap between those P and Q or any intersections, right? So this is how we remove the vulnerability. Now, if we, so our next phase is reduce or remove repetition in at least one of the subregexes P and Q that match a shared string. Now, what we can do here is we can say, OK, we have to match /W and /D consecutively, but let's say what? We'll do /W 15 times and /D 10 times. Or for star, we can say you can just say, OK, let's match /W/D up to 10 times. So there is ambiguity here, but we are just limiting it to a certain number. So it will not be infinite. So this is how we are avoiding redos here. So we evaluated our anti-patterns and fixed strategies in multiple ways. I will present two experiments today, but there are more in the paper. So evaluation 1 studies whether our anti-patterns accurately identify vulnerable regexes, and evaluation 2 studies whether our anti-patterns and fixed strategies help developers better understand the outcome of the detection and fix tools. So let's see the first evaluation. So for this experiment, we used a dataset of 209,000 regexes. So we collected the ground truth of whether a regex is vulnerable or not using Weideman's automatic detection tool. So with this, we study whether our anti-patterns are as accurate as the automatic tools at identifying vulnerable regexes. So in this experiment, we compare our anti-patterns to the state-of-the-art anti-patterns that Davis collected in 2018. So although anti-patterns are expected to be used manually by humans, we applied each set of these anti-patterns automatically using scripts to be able to study such a large data set of regexes. So in this experiment, we measured the precision and recall for both of those techniques. And this is what we have found. So we see that our anti-patterns as a group are almost as effective as the automatic detection tools, as they detected 99% of all the vulnerable regexes detected by the automatic tool. Also, our anti-patterns as a group provided very high precision and very high recall compared to the state-of-the-art anti-patterns. Now let's see how we performed our usability study. So for this experiment, we asked 9 open source software developers to perform real-world redos detection and fixing. They performed the task over their own regexes from open source projects that they have contributed. So we had two types of tasks. The first one was detection, and second one was fixing. And for treatments, they at first used an automatic tool, an automatic fixing tool, and then the other treatment was the tool combined with our anti-patterns for detection and fixed strategies for the fixing. So we measured the success of our anti-patterns or fixed strategies as to see if there's any difference between understanding for the treatment 1 versus treatment 2. So for detection, we asked how strongly they understood what makes the regex vulnerable, using a Likert scale of very strongly, strongly, neutral, weakly, and very weakly understanding. So we see from our results that subjects using existing tools only reported very weakly understanding, and when they use our anti-patterns in addition to the existing tools, the self-reported understanding improved to strongly understanding. So for fixing, we asked them how strongly they understood what makes the resulting regex not vulnerable using the same scale. So subjects reported very weakly understanding when they use existing tools. On the other hand, when they use our anti-patterns and fixed strategies to complement the existing tools, their median understanding improved to very strongly. So in summary, our anti-patterns and fixed strategies complement existing tools with much higher understanding when fixing. So in this presentation, we first saw REDOS is a serious problem. For solving the issue, we provide a novel approach to improve the usability of existing detection and fixing tools. Our contribution has the form of an ambiguity theory, anti-patterns, and patterns to fix vulnerable regexes with high understandability. In our evaluation, we show our anti-patterns have very high precision and recall, and we also show that our anti-patterns and fixed strategies provide much higher understandability when detecting and fixing vulnerable regexes. With that, I would like to conclude my presentation, and now I can take questions. Thank you.
Thank you very much. If you have any questions from the audience? I think we're all slightly overwhelmed by your presentation today. So I come from the compiler world originally. So when you design programming languages, then you're trying to have LL1 programming languages that can be parsed top-down, and these ambiguities don't arise.
Yeah.
Are there any traditional compiler tools that do this kind of analysis on?
Yeah, so the compilers doesn't have this. So mostly the Regex engines are not built into the compilers. So every compiler has some Regex engines tools built into it, right? So what happens is most of the compilers uses a backtracking engine. So that introduces these kind of problems. So there are tools that can solve this issue. So what we come to is we complement the existing tools that can do this kind of analysis.
Okay, thank you. We do have one more question.
I wonder what's the level of expertise of the developers that you've used? Because aren't you afraid that the number of developers that you've experimented with is very small? And the second question is, what's the performance impact of your mitigation, and how can somebody use it in their project?
Thank you for the questions. So first of all, about the developer study. So there are two experiments in our paper. We showed the last one. So for this experiment, we found developers that have contributed to a vulnerable regex. So we found some developers from GitHub that had some vulnerable regexes in their repositories, right? So it was very difficult to find these developers, right? Because there are not many developers that have introduced those vulnerabilities. So we at first found those developers. So that's how we justify the number 9, because it is very difficult to find those developers and get them to, and even if you find those developers, get them to interview and make them fix the regexes using your tool is difficult. And what was the second question, please? Can you repeat that?
How do we use your mitigation in our own projects, and what's the performance impact?
Yeah, so the performance, so we basically provide more usability. So there are already existing detection and fixing tools. On top of that, we add more understanding for developers. So our rules would basically take a training session like of 30 minutes or 1 hour, and then you can train the developers. They would understand what the problem is, and they can then apply the rules or fixing strategies themselves when they use the tools.
Thanks.
Okay. Last call. No more questions. Thank the speaker again. Thank you very much.